what exactly I will talk and what are the contents of my talk. So all the summary I will not give because the summary itself is there in the title, Quantum Computing Fundamentals. So I will be starting discussing about some fundamentals. Okay, a person with no quantum physics or quantum computing background can easily understand through my talk and get some kind of a idea out of it. And at the end, I will discuss a few applications based on quantum computing and possible research opportunities thereon. Okay, right. So before getting into the fundamentals, first of all, we should know how one started working on quantum computing. What I mean is, who actually sparked the idea of quantum computing. So my slides consisting of a lot of text. Please don't worry about it. So this is usually I keep this content or a text in the prospect of students. So if the students reads through my PPT, you should be able to get the idea about 60 to 70%. So I will summarize what its slide is about. So in 1959, a great scientist and also a great teacher, Richard Feynman, a physicist, he hinted an idea of mimicking nature, means simulating nature using some kind of computing devices. Okay, in 1959. So that's a vague idea. In 1981, he said the conventional computers what were there by then were not like sufficient enough to mimic the nature, right? For example, how chemical reaction takes place, how a leaf converts the sunlight into energy, all those things, like nature wise, the activities, those things we can't mimic on a system or a model or a computer, right? Unless we can't mimic or we can't study, we will not get insight into it. So he said we better have some kind of a machine based on not based on some laws of quantum physics, not a regular physics, right? We have a classical physics, electromagnetic theory, and classical mechanics. All those things were there. So those are not sufficient. He said we have to get in little bit more, that is using laws of quantum physics, right? Hopefully, many of you at least got some idea about quantum physics during your earlier first or second years in the engineering. Okay, so that's the idea. And he gave a very nice talk in 1981, right? That actually sparked sparked a fire in many of the physicists by then to perceive the quantum computing based on quantum physics. So in fact, quantum physics started developing from 1900 and up to 1929 and 1930. It was full-fledged developed. Only thing is applications were not explored until then. Okay, so from 1980 onwards, the quantum computing, people started perceiving quantum computing went went on. Okay, so after that, in 1985, there's a name by David Dutch. He gave a first proposal, a theoretical proposal for realizing a first universal quantum computer. Okay, so some device which is based on physics laws which could compute. So that's his idea, 1985. So his model, whatever model he proposed, is purely based on some mathematical concepts, right? So equivalent to a Turing machine. So he called a quantum Turing machine, right? Which could model a quantum system, the real nature, whatever around us, right? So basically, what it consisting of? It consisting of two-state system. A system can exist in multiple states, right? If I take a glass of water, if I heat it, it can exist in hot state. After some time, if you leave it somewhere, it will cool down. So it will go into cold state. Okay. So the system which David Deutsch is proposing consisting of two states simultaneously existing. We will get into that. What are those two? What are kind of states? Okay. The moment he took the two states, he represented them in binary logic 0 and 1, right? Okay. So this two-state system will evolve in time, right? Just like water cools down after some time. The system also may go into some other form. So those things could be represented by this gate operations, right? So that's an idea. We are not getting to too much, right? So we are just trying to get how the progress of quantum computing or research of quantum computing is taking place. After 1985, the next big breakthrough is in the form of algorithms from the software side using a hardware effectively. So this was in 1992 by David Deutsch and Richard Joyce, right? So they proposed, they gave a first algorithm. What it does, it solves a problem with certainty in exponentially less time in comparison to conventional classical computers what were there by then. Okay, so that's a tremendous improvement. Okay, so later on in 1993, the Bernstein and Vajrani, they showed even when this quantum computers can have some kind of a error, okay, so even with that they can outperform the classical computers. That is also a very good advantage. Soon after that, Daniel Simon showed that exponential speed up is possible with the quantum computing. Okay, next. And people would say there is an algorithm by Peter Shor in 1994. In fact, it is called as a crown jewel of quantum computing. So what it can do is it can factor a large integer into two prime factors. Okay, that's in fact very commendable. Why? Because the current internet, whatever communication we are doing, is based on RSA cryptographic protocols, right? So that is based on the factorization of an integer, factorization of a prime numbers. Okay, so his algorithm he actually gave in 1994 could crack that RSA protocol within no time if he is provided with the adequate quantum hardware. So as of now, we don't have a full-fledged quantum hardware developed to have a proper Peter Shor algorithm implementation on it. But as the technology is improving, so down the corner, definitely we'll have hardware. So Peter Shor algorithm is going to make a lot of changes in the communication. Okay, so after that, another crown jewel of quantum computing is Grover's algorithm, right? He gave it in 1996. So basically, its ability is to search from unstructured data, right? And in addition to that, it can do with quadratic speed up. Okay, so exponential speed up was there with the conventional computers, and that could be like polynomial speed up, and it could be improved with the Grover's algorithm. Okay, so that from 1980 to about 1994, and lots of developments were happened. In 1996, Seth Lloyd proposed quantum algorithms which can simulate quantum mechanical systems. The moment if you can able to simulate a mechanical systems, you can explore ideas like drug design in pharma industry, right? So even in the cancer treatment also you can marvel. Okay, fine. So those are the developments, how the motivation of quantum computing is there from 1980 to 2000s. Okay, so if you look at the progress of research in quantum computing trends, so initial days it was very moderate, very slow in fact. Later on it picked up and it got a very steep increase from 1916 onwards, sorry, 2016 onwards. Okay, so you see a vast increase from 2018 onwards. Okay, so this is just a data until 2021. So lot of progress will happen from 21 to 22. Okay, right? So let me get into the fundamentals. Okay, first of all, what is a quantum computing? What is a quantum information? So to understand that, better to use whatever knowledge we have already, right? We have a classical computation, right? Most of you from computing background, so they definitely know what are the bits. Bits are zeros and ones, right? Okay, so how it is stored on a hardware, right? So the best hardware which can have in our palm is a credit cards, right? If you credit card, debit card, if you just take it out at the behind, if you see, there is a black strip. That is actually magnetically sensitive material. It's a magnetic strip. For example, it would look like this. Okay, so on that the bits 0 and 1 were saved. How it is saved? For example, if you take a location, a part of that strip, it's consisting of plenty of atoms, billions of atoms. Okay, let's take one atom and just look into it, what it is. Since it is a magnetically sensitive, means magnetically active, means there is a unpaired free electron in its outermost orbit, right? So that is the only one, the game changer. So it is rotating about its own nucleus. That means everything, all other electrons are paired and they're inside. Okay, they are not going to make any change. The one which is rotating or revolving about the nucleus at the end would constitute a current, a conventional current in the opposite direction to its motion, right? The electron is moving in this direction in a clockwise. The current would be in anti-clockwise, that we know. The moment there is a current going in a loop, obviously a current carrying loop will execute a magnetic field. What is that magnetic field for this loop? Obviously it is pointing upwards. We can use right hand thumb rule and get to see, for every electron, a free electron revolving about an atom, its nucleus would constitute a magnetic field, which we will call a magnetic moment, right? So by default, you can arrange these magnetic moments in required manner, right? So what I will do, I'll bring some artificial magnet which can send a magnetic field lines, so I can align these magnetic moments according to my requirement. Okay, so let's say in this strip region, all the magnetic moments were aligned towards my left. That means that is a one way of storing my data. On the other side, another other piece, I will store it towards left, and the next piece I will store it to the right. So in this way, I can store the information of, let's say this is 0, 0, and this is 1, right? In this way, the information is being stored on a magnetic strip, right? So not only along the strip, you can also store the information vertical, right? Vertical to the strip. So you can follow different mechanism how to do it. It's again engineering aspects where we are not getting into it. So what is the idea we are taking from this slide is the information of bits, classical bits, is stored on a magnetic strip or a magnetic hardware using many atoms at a time. Okay, so not a single atom, there are many atoms in the strip which would store information of 0. Together they constitute as information of 0, right? So it requires lots and lots of atoms to store one bit. Okay, how it is done in the case of quantum computing, let's see. Okay, so for quantum computing, what people do, they will just take a single atom itself. Okay, so single atom means there is a nucleus, there are orbits around the nucleus. Okay, so I will take like a conductor atom where there is a one free electron in its outermost orbit. All right, so if I supply an energy by sending some photon, this electron can jump into outermost orbit. Obviously, it is held up by Coulomb force of attraction to the nucleus, so it was stuck with some thread. So if I supply some energy where I can break the thread, or I can elongate the thread, I can stretch the thread a little bit more. So that means I'm allowing the electron to go away from the nucleus. So I'm supplying a photon, right? So at atomic level or a subatomic level, if I supply a photon, this electron can absorb that energy and go to the outermost orbit, right? Interestingly, this electron will not always excite to outermost orbit. It will not always absorb the energy, right? It will not absorb the energy and it will stay back in the old orbit. Okay, so this is a beauty of the nature. By default, nature has given this ability for subatomic particles at a quantum level, means atomic level. Okay, so when I supply energy, the entity which is supposed to absorb the energy may absorb or may not absorb. So in that case, there is the only way to explain that situation is using probabilities. What I mean is, if I take 100 atoms, supply 100 photons, 100 all like atoms, supply all 100 like photons to those 100 atoms, right? So out of 100, only 60 of them will absorb, and 40 of them doesn't absorb. That is happens, right? Another way of understanding that experiment is take a same atom, shine the photon to that atom 100 times and see how many times it will absorb, how many times it will not absorb. The single atom can absorb 100 times, and out of 100 it will observe only 60 times, and 40 times it will not observe. So you are performing 100 times experiment. Okay, so that is what happens in quantum regime, means quantum level. Okay, so the only explaining that thing is through probability, that notion of probability. So let me get into the little bit more into it, how the probability nature would lead to a different area or different description of quantum physics. Okay, so it is in fact called quantum ambiguity. Okay, so here, if electron is there in this orbit, it is rotating in this orbit. At any given moment, I can't specify its location, I can't specify its momentum with accuracy because it's so tiny. It moves possibly with a very good velocity, so I can't specify its location with 100% accuracy. There is always exists some kind of error in the position as well as in the momentum, right? So that means the only way expressing that kind of inaccuracy or inadequacy in explaining things is through using the waves, right? What I mean by that, let's concentrate on only this side of the figure. Let's take, there is a nucleus, there is an orbit, right? There is an atom rotating about the orbit. Okay, now for us waves means what? If I just go to a lake or a pond, I'll just drop a stone. From the point where I drop the stone, from that point waves will emerge, right? From that point the waves will emerge and they spread and they go far and they may die down later on. Okay, so if I ask you where is the wave located, you would say it located everywhere. From the point you drop the stone, from that point, from the point where it will dies down, so it is located everywhere. So if electron is not stably located at one point, it is non-localized, it is everywhere. In that case, the only way to explain or express its position or its momentum is through using the waves. So people came up with an idea that if I take an electron and assume that electron behaves like a wave, then everything makes sense, right? So with that, the quantum physics, when it is developed in 1920s and people started giving explanation for quantum particles, something at the atomic or subatomic level would behave like waves as well as particles. So it is called wave particle duality. So an electron in an orbit would behave like a wave. What is that wave? So if I suppose, if I just draw a wave on the orbit, right? Okay, so I'm sorry, it would look like this. Okay, and there is one more wave exactly opposite phase, right? So basically what I'm trying to do, I'm trying to put a standing wave pattern on this circle orbit. Okay, so for every orbit, if there is an electron, there is some kind of a wave associated with that electron. Okay, so suppose if I have 3 orbits about a nucleus, right, there are 3 electrons revolving around that in each orbit, so I can have a wave existing in those orbits. So the best way to understand is, let's say if I have a tape, some kind of a tape, I put a tape with a circular fashion, some kind of a disc manner on each orbit. So on the tape there exists a wave, right? So if I just cut the tape and straighten the tape, what I will see, on the lowest orbit there may be one single wave confined, one wave with a single wavelength confined, and the next orbit there may be 2 wavelengths confined in that orbit, and 3 wavelengths, and so on. This is what usually happens when I take an atom. There exists an electron getting associated with some kind of a wave in that particular orbit. Okay, the moment I bring in the idea of a wave, obviously wavelength is there. What is a wavelength? So very simple. So it is called a de Broglie wavelength associated with a quantum particle, so which is equal to the the Planck's constant divided by the moment, linear momentum of that particular particle. Okay, fine. So the wave nature would express why a quantum particles would not specify or are not localized to a particular position. They exist everywhere because they behave like a wave. Waves are the ones which exist everywhere, right? Okay. So mathematically, we know pictorial representation of the wave. The best way to represent this is using some mathematical function. So we will call that as a wave function, representing by a Greek letter psi. Okay. So let me get in how this wave function could be used to realize quantum memory. Okay. Whatever we are straightening out here, we'll just take that same waves and put it here. We will call it three different kinds of states of a given atom, because atom can exist in lowest orbit, outermost, and much outermost, the electron. Okay. So the lowest orbit may have half the wavelength confined in that orbit. One wavelength, 1.5 wavelength may be confined in that orbit. Okay. How this wavelength is connected to electron's presence is very simple. We just take a wave, it's a mathematical function, and if you take the modulus and square it, and what you will get, for this corresponding wavelength wave, there is a hill. For this one, there are 2 hills. For this one, there are 3 hills. Okay. So wherever there is a peak, at that point, if you find out the value, you will get some value, maximum value. That is in fact correspond to the probability of the electron presence in that location. Means at this point, the electron could exist with high probability. Wherever there is a node, you see, this is a point where there's a wave is hitting the node, the electron is having no probability of existence in that location. Okay, so that means electron can exist here with some more probability, here with more probability, and here in the more probability if I take a third orbit of an atom. Okay, so what people did, people started exploring these 3 possible maximum possible probabilities to realize quantum states, and those quantum states could be used to store the information in the form of bits. All right. So interestingly, when I take this third orbit, atom can exist in 3 states at a given simultaneously. Okay. So those 3 things could be used to realize a quantum states. Not only this, I can take 2 states together. Okay. So 2 states together, I can again realize multiple states, multiple information storage locations. It's like I'm having an almirah with multiple divisions where I can store my data information. Okay. So with a classical physics, what is the idea? I will have one almirah. Okay. One almirah with only one division. I can store only 1 bit information in that. But when I go to quantum level, a single atom can allow me to store multiple bits in a given almirah. Right? Okay. So that's a very good, simplest example where we can understand how the quantum memory is realized. Okay. So this is for the atom, right? Multiple locations of an atom, multiple possible locations for the electron. Okay. So this is in just 1D. What I can do, this is a 1D equation. This is a Schrodinger equation, time independent Schrodinger equation. Okay. So if you solve this, you will get this. And if you find the modulus, you will get this. The similar way, I can write Schrodinger equation for a 3-dimensional system. Means a 3-dimensional system means in a space, if the electron is there in a box, right? A box means some kind of a potential box with a U as a potential. So this is the equation governs that system. So where E is the energy of that electron, where it can exist. Okay. So if I solve by assuming the box is having 0 potential, possible. Okay. And I will get a solutions like this. What is the energy corresponding to this particular solution? Energy corresponding to this state is this one. So we are not getting into the details. So where L, Lx, Ly, Lz are the dimensions of the box. Okay. Nx, Ny, and Z are the quantum numbers associated with this particular atom. Okay. And H is a Planck's constant, M is a mass of the electron. Okay. So this is a 3-dimensional solution. If you solve it for a particular atom, hydrogen atom or any other atom, what it would give us something like this. Okay. So for the lowest orbits, what are the possible electron locations are dotted like this. So as you go away from the nucleus, you will get many dots. Okay, let's take hydrogen atom. About the nucleus, there are plenty of plausible locations where electron can exist with maximum probability. Okay, so please don't confuse with all the dots as a electrons. They are the possible locations of the electron. So how it is described? Using some wave function x, y, z. Okay, so I can't specify electron's position accurately. There is always error. There is a momentum error always when I measure. So if I just take a product of it, that product cannot be less than the Planck's constant. It is always more than the Planck's constant. Okay, so that's a uncertainty principle, right? So people explore this idea to realize quantum memory. Let's see in the next slide. Okay, so we'll get back to the same semi-classical picture where the atom is there with multiple orbits. I will send a photon of some energy, which can have any amount of energy. So that photon will come, supply energy to the electron, may go from lower to outer, or electron from the outer orbit can jump into the lower orbit by some spontaneous emission and emit some photon. Okay, so that is possible. So what I will do, I'll just take a snapshot of this small region and just write it here. Always I can't write this circles, right? Orbits. So what I'll do, I'll just take a part of it. So the one which is close to nucleus, I will call it as a ground. The one is away from the nucleus, I will call it as excited. When I supply a photon that can absorb, electron can absorb, it can stay in the excited state for some microseconds. After that, it can't stay ever for an excited state. It always goes down to lowest state. So that's a nature. Nature always tries to acquire a least possible energy state, stable steady state, right? So the photon is emitted. Okay, so during in between, if I just observe this entire system, it appears to me like electron exists even here with some probability. Okay, so that means there are probability numbers about, let's say, 60% excitation, 40% not excitation. Those things I can use it to store 2 bits of information, that is 0 and 1 at a time on a given atom. Okay, so that's how quantum memory is being realized. Not only that, I can take one more orbit. I can store 3 bits of information on a single atom, right? It's called a qubit. Okay, quantum bit means storing 2 bits of information on a given atom. Qubit means 3 states saved on single atom with 3 orbits used. Okay, right? So the possibility of realizing a quantum qubit on an atom is using the orbits. Okay, not only that, atom can exist, atom with an electron can exist in 2 different states. How? If electron can be in ground or excited, that is one way. Electron can be exist with upspin or a downspin. There is something called spin. What I mean by spin, if I just take a solar system, let's take our Earth itself, apart from it rotating about the sun, it also revolves about its own axis. So because of its rotating about its own axis, you may say there is a spin associated with that. Okay, if there is a clockwise spin, we'll have one kind of a representation, anti-clockwise another way. So similarly, electron can have spin. Okay, so one way of spin is represented as a one state, another way of spin is represented as another state. Together, that can create 2 possible states, because at a given time, at a quantum level, electrons, means subatomic particles, always exist in multiple states with some probability. Okay, so with upspin it can exist with some 50% and downspin with 50%. Together it can be 100%. So those 2 states could be used to realize a quantum qubit with a 2 bits storing on it, right? Okay, fine. So let me put that on a paper. Okay, so basically I'm writing a quantum state with a Greek letter psi representing a wave function corresponding to an electron being excited or not excited. Okay, let me do that. 40% not excited, 60% excited. Okay, that's what I'm writing. Okay, together it should give me 100%. Okay, I'm trying to write that way. Okay, so basically, what is a wave function for an electron? It's a wave. How should I represent a wave? Using some cos or sine function with some position and time dependency, right? So this is a wave function for me. But what I'm writing a wave function for an electron, whether excited or not, is this. It doesn't make any sense. This is making sense because I have a wave. I take a modulus and square it. I'm getting a maximum possible location of electron at here, position wise, right? But this is not making any sense. So it will make sense when I bring in a scientist Dirac notation. Okay, what is the Dirac notation? Let me tell you. Okay, so use the angle brackets, left angle and the right angle. In between there are vertical lines, right? So right vertical line and right angle, he called as a is called as a ket. On the left hand side, left angle and the vertical line, he called as a break. Together it made a bracket. Okay, there is a C in between, that is maybe correspond to some kind of operator. We will come to that later on. Okay, so he introduced this bracket notation to make or to bring a sense out of this equation. Okay, what is this equation, which is not at all making any sense? So with the Dirac notation, let me write down that same equation. What I'm writing is psi inside a ket notation, this is called a psi ket, is equal to not excited, I'm writing in a ket's notation, not excited ket plus excited ket. Okay, so for 40% and 60%, these are the probabilities. I'm writing, instead of that, I'll writing alpha and beta. Okay, so what I mean by writing alpha and beta is, if I just square alpha and beta and sum them, I will be getting 1. I will put a constraint that by doing it, what I'm saying is alpha square, that is alpha modulus square, and beta modulus square describes me the probabilities. What are those? Alpha modulus square is correspond to 40%, beta modulus square will correspond to 60%. Okay, now it will make sense for me, even though it will not explain the same waveform, right? So this quantum state representation in the Dirac notation would explain, at least there is an electron can excite with probability alpha square, not excited, and with the beta square it can be excited. Okay, so this is a Dirac notation for us. So the idea of bringing in Dirac notation is, somehow we wanted to write this quantum state in the form of some vectorial notation. What is a vectorial notation? For me, a two-dimensional vector R is xi plus xi plus yj, right? That we will see in the next slide. Okay, so a two-dimensional vectoral interpretation of quantum state, that's what we are trying to understand now. So let's take a two-dimensional vector for us. R is equal to xi plus yj. What are I and j? I and j are the base vectors which will describe me x direction and y direction. Okay, so for me, I wanted to have x of particular value, y of particular value, so that x square plus y square should be 1. So what I'm doing, I'm confining myself on a unit circle. Okay, right? If the radius length is 1, so I am confining myself on a unit circle. So in that way, I'm trying to correlate or relate my two-dimensional vector to this quantum state. Okay, so instead of writing not excited and excited, let me write not excited as a 0, excited as a 1. Okay, bring in the same constraint that alpha square plus beta square is equal to 1. That is, always the probability should sum to 1. Okay, that makes sense for me now. Now, if you see, relate these two equations, this is a quantum state, this is a vector. Okay, so is it possible to call this as a vector? When it is possible, wherever there is a 100% one-to-one correlation exists between this and this, then I can call it as. Okay, basically there are base vectors I and j. What are the base vectors for this? 0 ket and 1 ket. Okay, that makes sense. And what are the base vector multiplication exist in two-dimensional vector space? I dot I is 1, j dot j is 1, I dot j is 0. The scalar multiplication or dot product multiplication I'm talking about. So there should be some kind of a multiplication exist between these two base vectors, which should have a correlation to this, one-to-one correlation. Okay, what is that? A kind of operation between 0 ket to 0 ket should give me 1, 1 ket to 1 ket should give me 1, operation between 0k to 1k should give me 0, right? So I'm just trying to see. If at all, if that exists, I can call whatever space created by this kind of a quantum vectors, now I'm calling a quantum vector, would create some kind of a space. So a two-dimensional vector of this will create a space of unit circle. All the points on the unit circle were spanned by this vector. Okay. Similarly, this vector will span some kind of a space, a two-dimensional space. Okay. So that space is based on this base vectors 0ket and 1ket, just like ij, right? With the operation of dot product here, there should be some operation here. Okay. So right now I'm giving a name for that operation, some kind of a inner product. I'm naming it that. Okay. So let me understand that. Okay. So the inner product in the next slide. Okay. So to understand that inner product, multiplication or some kind of operation existing between the base vectors of a quantum state, right? 0ket and 1k. Okay, so the best way to do that is bringing in the matrix interpretation. Okay, so what is that matrix interpretation? Obviously, we have in a binary version 0 and 1. So I can only take 0 and 1. So 0ket I will represent as a column vector 1 0, right? 1ket as a 0 1. Okay, so this is a one statement and this is another statement. Okay, so there is no multiplication here. Please don't confuse. 0ket is represented as a column 1 0. 1ket is represented as a 0 1. Now, if I have that kind of a interpretation, let's see what is its corresponding transpose of this 0ket. Obviously, it is a row vector. A column transpose is a row vector. Similarly, 1ket transpose is a row vector 0 1. Okay, so for me, when I introduced a bracket notation, the transpose of this is a transpose of a ket is a bray, right? Obviously, right angle. Mirror image is a left angle, right? So that's kind of a interpretation we'll do. So here, 0ket is this, 0 bray is this. Now, a multiplication between 0ket to 0ket is not possible because it is in a row. I can't multiply, sorry, it's in a column notation. I can't multiply column to column itself. So the only way is convert one of them into row and then do the multiplication. Means a matrix multiplication is only happens when I have a proper order. So what is that proper order? If I have in order to have a 0ket multiplication with a 0ket, I have to do the transpose to the left hand side, left one, and then do it. Okay. So transpose of this one gives me bray. So bray multiplied to ket is the one, the multiplication wise that we will see. A bray is a row and ket is a column. If I do the multiplication, I am getting 1. That's nice. So the first condition is satisfied. So there is a 1-to-1 correlation between this equation and this equation. Similarly, you can cross check. 1 bray multiplied to 1 ket gives me 1. A 0 bray multiplied to 1 ket gives me 0. Super. We are getting a very good interpretation or kind of a relation to a two-dimensional vector to quantum state even at the multiplication at the base vectors. Okay. Fine. So when I introduced matrix interpretation for this kets and bray, it makes sense for me. Now, by doing that, I can also get a matrix interpretation for a given quantum state. What is that? Replace 0 with its corresponding column, 1 ket with its corresponding column, and find out what is the corresponding quantum state representation. That is obviously alpha and beta row, beta column. Okay. So what is its bray? That's a transpose of the column. Sorry, is a row, right? Okay, bray psi is alpha beta row. Okay, so with that we can do on paper the quantum computation. Okay, so this is a geometrical interpretation. Means obviously for a two-dimensional vector I have a geometrical interpretation, right? So is there a geometrical interpretation for a quantum state? Of course, yes. That is actually described by something called a block sphere. So it's very simple. If you just take a three-dimensional three-dimensional sphere, on the surface we will have a two-dimensional surface on that sphere. Okay. So it's like if you take a football, on the surface of the football, we'll have a space. That space we can use to represent a quantum state, right? Okay. So how I will connect? I will connect alpha and beta into some thetas and phis, where theta is the polar angle and phi is the azimuthal angle, which exists on the equatorial space, right? If I just slice this ball at the middle, I will have a space, right? Equator. So on the equatorial plane, on a disk, I will have an angle, right? So that angle is a phi, it's azimuthal angle. I can connect that angle, and the polar angle means if I have a point on the surface, connect that point to the origin. So that vector, the position vector of that point would make an angle with the north pole. So that is a polar angle alpha, a theta. So if I just drop a shadow of this line onto the equator, so that will make an angle phi with an x-axis. So that is a azimuthal angle. So I can convert alpha, beta in terms of those angles. How do I do? Alpha is cos theta by 2. Beta is exponential I phi sin theta by 2. Okay. So for example, if I just take a theta equal to 0 and phi doesn't matter, because when theta equal to 0, cos theta by 2 is 1 and sin theta by 2 is 0. So I'm talking about the north pole, a point on the north pole. So now a quantum state means atom being in the ground state, I can represent as a north pole with a 0 kit, not excited state. Okay. If atom is excited, I will take theta to be pi, and phi doesn't matter because I'm talking about a single point. So any point other than north and south pole, everywhere else atom can exist in a combination of theta and 0 and 1. Okay. So in this way, even the quantum state could be geometrically interpreted on a surface, a two-dimensional surface of a sphere. Okay. So this is the equation representing a quantum state in some terms of thetas and phis on a block sphere, right? Okay. Now, why can't we go for high dimensional quantum system? Why we always wanted to have two-dimensional quantum system? That's not a compulsion, right? So how do I generate multiple quantum systems? One way is take multiple orbits, right? So a given atom can have only certain number of orbits, distinct orbits, which can be easily discriminated. Okay, so that's a constraint there. So what I will do, I will combine two quantum systems and create higher order quantum system. How I can do? Very simple. Just take one atom which can exist in ground and excited with some probabilities, and where alpha A and beta A are probability amplitudes. Similarly, another quantum system means another atom if I take, right, and put them in a box where they can interact. Okay, so when they're interacting, mathematically, how do I represent their interaction? I represent by some tensor product. Okay, psi A tensor product with psi B. By the way, I know what is the column representation or the matrix representation for atom A and B. Let me put it and take a tensor product. When I take a tensor product here, means take the first element, multiply it to both the elements, I will get first two elements of the product. Second element multiplied to the second entries, I will get another 2. Okay, instead of calling alpha A, alpha B, I will call it alpha 0, 0. What I mean is, this would represent both atoms are in the ground. This would represent one is in ground, one is in excited. Similarly, the remaining 2. The last one, if you see, both are in excited. So if I take two atoms which can exist in ground or excited, put them together, and if I see overall system from the outside, what I will see is 4 possible quantum states, right? Earlier, only 2 possibilities for a given atom. Combining 2 atoms, I'm creating 4 possible quantum states. Okay, so in this way, I can store 4 bits of information on 2 atoms. Beautiful. Okay, so 4-dimensional quantum basis is for me now is 0A, 0B, 0A, 1B, 1A, 0B, 1A, 1B. Always no need to write a subscript, so you can have it in your mind. So first one correspond to atom A, second one correspond to atom B. So in this way, this is the basis. By the way, what is the basis for 2-dimensional quantum system for me? This one. Okay, by combining 2 atoms, I am creating 4-dimensional quantum system where it can store 4 bits of information on a given setup. Okay, so if I add one more atom of this kind, let's say side C, right? So that will allow me to store 8 bits of information. So where I am generating 8-dimensional quantum system. So that is 2 to the power of 3. So in this way, higher dimensional quantum system could be exponentially increased, 2 to the power of n. If I just take 2 to the power of n, I'll have plenty of quantum possible storage locations. Okay, so with an n 2 to the power of 50 or 2 to the power of 60, you can have as large as the number of atoms in the universe. So it's so large. Okay, so classically, instead of using multiple atoms to store 1 bit of information, right, if I start taking 1 atoms to store 1 bit or a 2 bit, right, and generate higher dimensional quantum system in that way, with just 50 to 60 atoms, I can store lots and lot of information at a quantum regime. So only the confinement is you have to restrict the atom to exist in quantum regime, means multiple states. Okay, so this is a matrix interpretation for high dimensional quantum system, how it would look like. I'm not getting too much into this, so it's a simple interpretation. Okay, so let's get back to the operations between quantum states, right? So just let me check how much time I have. I have another 10 to 15 minutes, I think. Okay, I will go a little bit fast.
Yes, sir. Sir, take your time. No problem.
Yeah. Okay, so the operations between the quantum states. Obviously, if I take a bit, right, I will do some operations on it. It will has to change it to some other form, right? So even the quantum state should also make some kind of changes from one form to other form. So given atom being in this quantum state should change it to some other form. Okay, so what is the best operation which we know from the classical computation? The first operation which could come into our mind is the NOT operation. So if I send a 0 into NOT gate, it will convert to 1. Or if I send 1 into NOT, it should become 0. So it's a negation. So the question is there a NOT gate in the quantum computation? Okay, if it is there, what kind of operation it would have? Okay, so obviously a quantum state means multiple state existing form. It's in the superposition form, right? So if I send a superposition into the NOT gate, 0 becomes 1, 1 becomes 0, right? What it means, it is interchanging the probability amplitudes. Very simple. If you see, if I have an atom with existence of 60% probability on excited, 40% on the ground, if I send that atom through a quantum gate, I will get a resulting atom with the probabilities interchanged. Means when it comes out of a NOT gate, what I see, atom now is in 40% in excited state, 60% in the ground state. So there's some kind of a 20% loss in the excitation to ground that is being happened. Okay, right? So that could be a one possible gate operation in the quantum computation. Okay, since we are talking in terms of matrix representation for a given quantum state, obviously there will be a matrix representation for that NOT gate. Okay, what it would look like, you can simply guess it. So a matrix representation for this psi, the old state, is alpha beta rho, and after the operation, not operation, the operation is the state is beta alpha. So I have to interchange the column entries, first to second, second to first. So what is the possible quantum state? What is a possible matrix operation? It is a 0 1 1 0 matrix. It's a 2 by 2 matrix. With the trial and error method, you can guess it. Okay, so this matrix would correspond to a NOT operation here. Okay, right? So a quantum NOT is not just like any NOT in classical computation. Classical computation NOT gate operates on only a single bit, but in quantum operation, a NOT operation would act on a superposition state where the probability amplitudes are interchanged. Okay, the corresponding matrix exists. So now we can confirm that the quantum operations will be always represented by matrices that is given, because we have to do something with the columns. The columns are one-dimensional matrices, right? Okay, so the matrices would do operations on the column. So that is one thing. Now there is a one constraint for me, a given quantum state. What is that? The probability should sum to 1, that is alpha square plus beta square to 1. obviously the resulting quantum state is also having alpha square plus beta square is equal to 1. All right. Okay. So if I see, the quantum operation always preserves the nature of the quantum state. It is not pushing the quantum state out of to some other form. Okay. It will always remain in the quantum state. Okay. So if it does something else, it is called a measurement. We will come to that later. Okay. So there is always exists a constraint on the matrix also. What is that matrix? A constraint. Okay, if I just take that matrix and then take self-adjoint, means transpose and complex conjugate, and multiply with that matrix itself, and if you see, what do you get? Identity. Okay, so a given quantum gate is represented by a unitary matrix. Okay, what is the unitary matrix? The matrix which satisfies this relation. Okay, so you can say other way around. Any unitary matrix could be possibly represent a quantum state, right? So from now on, we will try to associate some kind of a unitary matrix for a quantum gate. Okay, so the first thing is not gate. Let me go a little bit ahead and see what are the other possible gates we can have. Okay, other possible gates is, suppose if I have a quantum state like this, if I want to change the phase of beta, okay, I want to make negative b. Okay, let's say there is some quantum gate, okay, which gives me alpha beta to alpha minus beta. Okay, so by trial and error method, always you can guess what is the corresponding matrix. That is identity matrix with just a second, the last element is replaced by -1. Okay, so that is called a Z gate. It is a phase gate. It induces a phase to the excited quantum state, excited part of the quantum state. Okay, right? If you want, you can always cross check whether this Z gate or a Z matrix is unitary or not. Take this matrix, find its adjoint, complex adjoint, and multiply. And if you get identity like here, then you can use that for the corresponding quantum gate. Okay, so again, this is also a single quantum qubit or a quantum state going in, coming as a single qubit, right? So I'll ask you a question. How do I get this superposition? First of all, right? If I take an atom, either atom electron could exist in one of the state or it can exist in another state. If I look at the room temperature, okay, but if I confine it to some kind of a ideal location where it is not interacting with the environment, cool it, and then supply a photon, right? An atom can be in ground as well as in excited with 50% probability, right? So that is possible, in fact, in the engineering terms. That means I can always have a matrix operation on a given ground state or an excited state. Okay, so the matrix operation acting on that single state creates me superposition state. Okay, so how it is possible? There is a matrix called Hadamard gate or Hadamard matrix. So if you multiply Hadamard matrix, which is happen to be 1 by square root of 2 multiplied to 1 1 1 minus 1. Okay, it's a matrix, 2 by 2 matrix. If I just take that matrix, multiply this matrix, means add that Hadamard matrix onto 0 ket, which is happen to be a classical state, means atom is in strictly in ground state. If I act Hadamard gate on the that kind of a quantum state, what I'm getting? I'm getting 1 by square root of 2, 1, 1 column. What is that? That is a superposition state with 50% probability in both ground and excited. Similarly, if I act Hadamard gate on a single state 1, that excited state, I'm creating a superposition state with a negative phase for the excited part. Okay, so by acting a Hadamard gate on a classical state, I am creating a superposition state. Means a qubit is created from a ground state or an excited state of an atom. Okay, right? So again, you can cross check whether the H gate is unitary or not. Obviously, it is happen to be unitary. Okay, so in experiments, how people creates a superposition state is take the atom, isolated atom, right? Shine a photon onto that. So they create a superposition state. If I have to represent the same process on paper, I will take that particular atom ground state as a 0 ket, and the supply of a photon I will represent by Hadamard gate, and photon getting interacted with a atom is represented by Hadamard gate, means Hadamard matrix operating or multiplying to a 0 ket, okay, giving me the superposition state. Okay, so if you see, Hadamard gate is a very useful quantum gate which allows me to create a superposition from a classical atomic states. Okay, fine. So there is another way of representing the Hadamard gate operation. Okay, if I take a ground state along the x-axis, excited state along the y-axis, if I just take on a two-dimensional surface, okay, I just draw a unit circle. Okay, if a given atom is there along the excited, if I act a Hadamard gate, okay, so this vector is slightly leaned towards the zero vector, zero state. So it is exactly in the equal position, means 45 degrees, it is aligned towards the 0 ket. Okay, so that is a Hadamard action. Okay, fine. So rotation wise, you can always use gate operations. Okay, you can also see other way around. Any rotation matrices could always possibly represent a given quantum gate operations, right? Fine. So far what we have seen is a single gate operation. Single qubit goes in, single qubit comes out. So that is not always the case, though we will have multiple gates going into some kind of a quantum gate, and gets me some kind of output. Okay, so what is the first possible multiple qubit gates is two qubits going in, coming out with some other form. Okay, right? The first thing is controlled NOT gate. What I mean is there will be a NOT gate which is controlled, means it can be having an effect or not having an effect depending on some kind of control. Okay, so suppose if I have a two bits, right, two atoms, both are in the ground. If I send the quantum state of the two atoms through a quantum gate, I'll be getting the same quantum state. What I mean is the control, which is 0, so will not have a change on the target. The second one is the target, first one is the control. So the C0 gate doesn't have any effect on 0, 0. When it will have effect? When the control is 1, the target is being flipped to 1, right? So that is 1, 0 becomes 1, 1. 0, 1 will remain 0, 1. If I send 1, 1, because control is 1, target should be flipped. It will become 1, 0. Now, if I just take a truth table and look at it, right? All these things, if you put it here and see, in fact, this is equivalent to XOR operation in the classical computation. Okay? Not only that, if I say control is A, target is B, if I generalize this entire thing into one single equation, so that would be equal to A comma B ket acted upon by C0 gate gives me A remains the same. You see, the control always remains the same. Target is being flipped with whatever the presence of the control. So which is B addition modulo of A, right? The XOR operation. Okay, so a C0 gate operation is in fact equivalent to XOR operation. Okay, so you can understand in that way, right? So let's see other higher dimensional quantum gates, right? So before getting in, what is a corresponding matrix representation? We know that for every quantum gate there is a matrix representation. Obviously there will be a matrix representation for C0 gate. Okay, so that would be, again, you can by trial and error method you can guess, right? So there will be 4 quadrants. Obviously it is a two-dimensional, like a two systems, means 4-dimensional matrix, the 4-dimensional quantum system. The matrix would be 4 by 4. The first quadrant is identity, second quadrant zeros, third quadrant 0, fourth quadrant is NOT gate representation. You see, right? Okay, so if you have this kind of a matrix acting on 0, 0 ket, we just saw what is a corresponding column representation for higher dimensional matrices, right? Higher dimensional quantum states. 0, 0, its corresponding is 1 followed by zeros, right? 1, 1, all zeros, last one is 1. Similarly, you can see for this much n dimensional quantum system, right? All zeros followed by 1 would be corresponding quantum state. Okay, so the C0 gate operation you can just cross check with this matrix on the corresponding column representations of 4-dimensional quantum basis, and you will get that. Okay, so the symbolic representation in quantum computing is we'll have lines corresponding to each quantum qubit. Okay, so there is one qubit is traveling like this, another is qubit is traveling like this. So you may ask, sir, qubit is an atom. How atom would travel? Okay, so for communicating, for traveling information from point A to point B, means atom A to atom B, what I'll do, I will use a photon. I will shine a photon. The photon will extract the information of the atom and it will travel along and go to some other atom and will just drop the information. It's like a postman between two different points, right? Okay, so now this is a qubit transition, this is another qubit transition, this is a control qubit, this is a target qubit. The C0 representation is written as a dot stands for control going to the next qubit with a plus sign, addition modulo sign. Okay, this is a C0 gate representation. Okay, right? So from now on, we'll have a matrix representation as well as symbolic representation for a given quantum gate. Right? Let's get back to the classical computation. We have gates like AND, OR, NOT. Combination of this, I will have NAND, NOR, and XOR. Okay, so typically what you observe in all these classical computation gates is whatever input is coming develops me some output. If I wanted to know what is input, I can't get back. So the reversibility is not there. Okay, so I will lose the information while I produce the output. Okay, so the output is produced at the cost of loss of the old information, right? But that will not have that kind of a scenario is not exist in the case of quantum gates or quantum operations. Why? Let me check. I will act Hadamard gate on 0 gate. I will get a superposition. I will act again, means I am acting two Hadamard gates by one on a 0 gate. What I will see, I will get back the same quantum state. Okay, so what I mean is if I act a quantum gate twice, I'm not doing anything to a quantum state. That is beautiful. What I mean is always I can come back to old state and restart again. So the loss of information is not happening in the quantum computing. So that's a very good advantage in the case of quantum computing, the reversibility of quantum gates, right? So that means I can realize multiple operations using a C0 gate with other single quantum gates, right? And whenever I needed, I can come back always to the old states, the initial parts, and restart my calculation if I am doing something wrong in the process, right? Okay, so one example for creating interesting quantum states from two kinds of gates. So let me take two qubits, both means two atoms, both are in the ground initially. For a one atom, I will act Hadamard gate, means I will supply some energy. For together, I will act a C0 gate, control NOT gate for first and second qubit. Okay, so if I represent on paper that action, what I will be getting is 0 0 ket plus 1 1 ket divided by square root of 2. So what I mean is both atoms could be in the ground or both atoms could be in the excited with equal probability, which means 50-50% probability. That is one kind of an option. If I have both atoms initially in the ground, if I send them into Hadamard and C0 gate together, I'll be getting a kind of a quantum state where there exists a very good correlation between first atom to second atom. Okay, it's like they're entangled. Okay, they're correlated. They're not separable at all. physically you can separate them. Let's say atom A and atom B sent to Hyderabad and Bangalore. So if you do something with an atom in Hyderabad, atom in Bangalore is also going to show some kind of a change, right? So what I mean is, if I try to observe atom A, if it falls into zero state, means ground state, atom B also falls into zero state, means the measurement in Hyderabad forcing atom in Bangalore also to fall to the ground state. Okay, so this is called entanglement. So one idea of quantum computing is superposition. The next idea of quantum computing is important one is the entanglement. Okay, so if I measure the atom, one of the atom, if one of them falls to excited, the other one is also falls to excited state. So in this way, using Hadamard gate and CNOT gate, I can create entanglement between two atoms, right? So using this entangled atoms, we can do lots and lots of interesting things in quantum computing. One is quantum dense coding and quantum teleportation, right? So many things. Okay, so Hadamard gate and CNOT gate are the most interesting and useful quantum gates required for quantum communication. Okay, so when I say measurement, so I will be representing with some kind of a meter symbol, okay, with an arrow. So it means I'm just measuring it. When I measure, a quantum state always falls into classical form. So there is no quantum nature anymore exists in it. So I'm forcing, right? Forcing a quantum nature, dual nature to a strictly 100% probabilistic nature, classical nature. Okay, fine. So some other CNOT gate variants, if I take CNOT gates, 3 CNOT gates, arrange them in reversible order 3 times, so I can able to swap the quantum states. Okay, if there is a qubit 1, qubit 2, I can change their locations from interchange the location using 3 CNOT gates in reverse order. So it's called swap operation, just swap gate. Obviously, you can have a quantum state, quantum gate representation, matrix representation for that. We are not getting into it. And another CNOT gate variant is, okay, CNOT gate is controlled NOT gate, right? So I can have controlled unitary gate also. Instead of NOT, I can have some unitary matrix operation, which I don't know right now, which can be anything. Okay, so there are other matrix unitary gates exist in quantum computation. So something like Rx gate, Ry gate, and Rz gate, T gate, and S gate. There are so many different quantum gates. So we are not getting into it. All those things, in fact, are the hybrid versions of whatever gates we have seen so far. Okay, right? Z gate and X gate we have seen. Na? From that gate only Rx, Ry, Rz gates are being obtained. Okay, so classical gate operations also could be realized with the quantum gates. Beautiful. Okay, what are those quantum gates which can mimic classical operation? There is a Toffoli gate. What is a Toffoli gate? It takes 2-3 inputs, right? For one of the input, it will make a changes in such a way that I can have AND operation. Okay, okay, so even I can have a NAND operation, right? So what I have to do for the NAND operation is the target qubit should be 1, and we will give a negation for the A and B product. Okay, and even the fan out operation means even I can clone. Clone means if there is a single bit state Y, that bit state could be copied to another bit state. Okay, so the fan out operation, the classically possible, is also could be realized with the quantum states, quantam gates. So Y is copied to Y. Please remember, this is not cloning, this is just a copying. If the quantum, if this Y is a quantum state, that cannot be copied. If a Y is a classical state, then only it can be copied. Classical state means it is either strictly 0 or 1, right? If it is 0, doesn't matter, we already have 0, there is no need of copying. If this is Y is 1, obviously you will get 1 here. Okay, this is how even the copy is possible with the quantum gates when the input states are strictly a classical states. Okay, so let's get back to cloning. Is how cloning is not possible in quantum states. Like I said, if I have a classical version of the cloning, where input is a purely classical state. I can nicely copy to a zero state here. Okay, but in quantum computing it is not possible. Let's say it is possible. Okay, we will do contradictory, right? So there is a superposition state, there is a ground state, a qubit, and I will use a C0 gate, and let's see, that gives me output with a ZA 00 kit plus B 11 kit as per the C0 operation. Okay, this is the actual action of C0. But if a copying is possible, what I mean by that, if this is converted, this is also copied onto this, means I will have a two atoms of same kind, okay, in a box. If I have a two atoms of the same kind in a box, we saw earlier, the resulting state is a four-dimensional quantum state, right? With the A square plus AB and BA and B square with appropriate base vectors. Okay, but what is the resulting one? Resulting one is this. So when this is possible to this is possible to this only when AB is equal to BA is equal to 0, right? You can't have that condition satisfied. It is impossible to have that condition. Okay, so that means cloning is not possible in the quantum computing. Okay, if input state, one of them which need to be copied is a superposition state, it is not possible. Okay, if the input state is a single bit state, like a one state, one kit or a zero kit, you can easily copy, right? So a quantum nature cannot be copied from one form to other form. Fine. So all these things are very important in understanding quantum computing. The moment you understand quantum states, then you can have idea on what are the quantum gates. Using the ideas of quantum gates, you can realize how the quantum states transform from one form to other form. Okay, using the quantum gates in the form of some circuits, you can have quantum processing. Okay, so you can design some algorithms and have some kind of a change or the transformation of quantum states from one form to other form. Okay, so with that, I can devise a hardware and also the software to work and do some kind of a quantum processing, right? So let's understand hardware wise what is needed. Obviously, I need an atom whose electron can exist in ground and excited. That gives me two-state quantum system. So other possibilities are nuclear spin. Apart from electron, nucleus also rotates about itself. It can have its own spin, either up spin or a down spin. Electron, like I mentioned, and ion. If I take an ion, any atom, I can add an electron or remove electron. I create an ion. For example, you take a indium ion, right? Remove one electron, it will become a positive ion. That can exist in two possible states if I confine it to a location, small location. So that will give me a possible qubit realization. Electron is obviously a qubit resource for me because it can exist in multiple locations or multiple states at a given time. Electron in a semiconductor gallium arsenide. There is something called quantum dot. You can take an electron confined to a three-dimensional space or any subatomic particle into three-dimensional space. I create something called quantum dot, which can exist in multiple states at a given time. That is also a possible resource for realizing a qubit. Okay. There is something called optical cavity. If I just take a photon, send it into a cavity consisting of mirrors, like a Fabry-Perot mirror. So the photon will go back and forth between the mirrors. So at a given time, photon can exist in multiple states. The pattern of standing wave, if you take, or any other polarization or anything. Okay. So those possible states could be used to realize a qubit. Okay. Optical cavity is also a good resource for realizing a qubit. Okay. Microwave cavity, the microwaves inside a waveguide could be a waveguide cavity could be a possible resource for realizing a qubit. So the moment if you choose the hardware, it becomes easier for to design a software and work it on. Okay. So when I take this kind of hardware, always there exists some kind of constraints. What are those constraints? Okay, there is something called a coherence time, means the existence of quantum nature in that hardware, means at a given instant of time, how long the atom can exist in superposition, how long it can allow me to store a qubit information on that. So that is represented by a coherence time. Okay, let's say it exists for some time. Okay, how many operations I can do means there is always exist a limit on operation time on a given hardware. Okay, so the operation time, for example, if I take for electron spin, okay, it exists millisecond time in coherence, means it exists in quantum nature. For one operation, it takes me 10 to the power of minus 7 seconds. That means how many operations I can do on that hardware? 10 to the power of 4 operations. Very good number of operations. Okay, so among this list, if you see, nuclear spin allows me 10 to the power of 14 up to that many operations. Ion trap allows me 10 to the power of 13 operations. Okay, so on an outset, if I ask you which hardware you choose to realize a qubit, you might go the one with the large number of operations. Okay, but there is a catch there. So when you choose particular hardware, it comes with a limitation, something like the errors may creep in. Maybe it is fragile, vulnerable to the environment. So all those things are the ones which we need to keep in mind when you design a hardware. So the question is, instead of asking how to build a quantum computer, one should ask how good a quantum computer I can build. Right? Means you have to strike a balance between coherence time and operation time and the number of operations and the surroundings and the setup. All those things you have to keep in mind. Okay, fine. Okay, the current physical realizations. So I gave up possible hardware realizations, and what are the current physical realizations people are in the community is being using. There is something called a transmon, means some electronic circuit with inductance and capacitance, right? A series inductance and capacitance circuit is being used to realize a qubit. We will just little bit go deep into this. And there is a photonic quantum qubit, means a photon, we just saw earlier, photon can carry information of a qubit. So if that qubit is sent through some kind of optical fibers with proper setting, I can always realize some kind of a qubit realization with a photon, which can be confined within a space that can be processed to have some kind of quantum processing. Okay, so these are called photonic qubits. Okay, so other one is ion trap. I can use some electrodes and confine the ions within that electrode and send some photons, laser photons into that ions and do quantum processing, and whatever output I can always study using some photon detectors. Okay, so this is another physical realization people are pursuing quite a lot. Okay, so the recent means last 5 to 6 years, this area is picked up. This is called nitrogen vacancy in the diamond. So what I mean is, diamond has carbons. Okay, remove one of them, put a nitrogen there. Okay, so that nitrogen can exist in multiple states because of the structure. Okay, those things would allow me to store 2 bits of information. This is a bit advanced for this talk, maybe. That's why I'm not getting into the deep. So if I take any hardware, so the hardware should allow me to store 2 bits of information at a given time simultaneously. So if that is possible, I can do quantum computing with that by realizing qubit. So here you see in transmon case, okay, there are Q1, Q2, Q3, Q4 located. So that means this setup correspond to 1 qubit, which is 1 atom. This setup correspond to another atom, and this setup another atom. So something like that. Okay, to understand how the circuits, electronic circuits would mimic an atom, a qubit, we will see in the next slide. Okay, right? So for me, if we just take a naturally available atom, a nucleus, an electron, another orbital, a possible orbital for an electron. Okay, so if I put that on energy scale, semi-classical representation, there is a ground close to nucleus, there is an excited away from the nucleus, and other orbits much excited, and naturally the spacing between each orbits is not equal. That is a nature. Okay, please see that, it's very important. So equally spacing is not there between the between the orbits in any given atom. So they are spread unequally. whenever I want to talk between these two levels, whenever I want to send a photon having exactly equal to this energy separation, I'll be always only addressing to this, only talking to these two levels. There is no way the information is lost to another two, because those two levels are not spaced or separated with this much of energy separation. So when I choose an atom with the particular two levels for an interaction or a processing, I am always bound to have only those. Okay, so that's the one constraint. Always troubles in realizing or mimicking atoms artificially. Okay, let's see how the realization as realizing a natural atom artificially. Okay, so let me take an inductor, right, a capacitor, okay, and inductor and capacitor connected to some source. Okay, so there is a capacitor here, don't worry about that, let's say it is not there. So what is matters for me, there is an inductor and there is a capacitor. Okay, so LCR circuit, if you recall, right, LCR circuit is a kind of an oscillator. It oscillator in the sense the capacitor charges up and then discharges. Again, it charges up and then discharges. So it becomes some kind of a clock. It always rotates and comes back to same location charge wise, right? Okay. So at a given instant of time, if I look at this LCR circuit, the charge on the capacitor can exist in multiple states with certain amount of charge and some other amount of charge and so on. Okay, so those individual set of charge status I can always represent as some kind of a quantum state. Okay, so LCR circuit, even though there is no R resistance, internal resistance is there that I can consider as R. So LCR circuit is a kind of a atom mimicking entity. Okay, only difference from here to here is the energy levels are not equally spaced. Here in the LCR case, energy levels are equally spaced. Okay, what is the angular separation or the energy separation between this and this? It is actually dictated by omega LC. Omega is angular frequency, which is equal to 1 by square root of inductance multiplied by capacitance. Okay, so that means I have some kind of a resemblance between naturally occurring atom and a LCR circuit, the energies wise, existing in multiple energies wise. Okay, so only thing is, if I somehow make these energies are unequally spaced, I can exactly mimic the natural atoms. Okay, so in experiments, how it would look like, there is an inductor and there is a capacitor. Together I am having a circuit. Okay, this is a aluminum deposited on a sapphire, so that gives me a LCR circuit. Okay, now my next target is convert the equally spaced energy separations of the LCR circuit to unequally spaced. How do I do? Okay, so people started using, instead of inductor, they use something called Josephson junction, right? Let me tell you what is that. Josephson junction is, if I just take a semiconductor, two separate semiconductors are of same kind, bring them together so close, right? In between, I will have small insulator, okay, some small layer, or I can have air in between. So I'm not connecting to semiconductors, but I'm just keeping apart, or I will put some insulator in between, right? So then I connect this lead and this end to here. So the Josephson junction is formed, that is represented with cross symbol on the square. Okay, when a current tries to pass through, right? So this is a semiconductor. When I cool the semiconductor, I will have zero resistance, means very good superconductivity you will be getting. Okay, so how the superconductivity is possible is, if I have regular conductivity, means electrons will pass one by one. Superconductivity in the sense, somehow at the very low temperature, the superconductors inside a superconductor, electrons come together and form a pair called Cooper pairs, and they travel, and together they travel lot and lot, and they carry lot of charges. So in that way, we'll have very good conductivity, that is called superconductivity. So if I replace inductor with a Josephson junction, and see what are the energy states corresponding to that LCR circuit. Interestingly, Josephson junction acts like an inductor by nature also. Okay, so that's why I'm calling LCR circuit. In that case, if I just see what is the energy separation of that LCR, that is unequally spaced. Superbly, there exists a one-to-one correlation between naturally occurring atom and Josephson junction based LCR circuit. So in that way, people started realizing a naturally occurring atom on the electronic circuit. So that is called a transmon, right? Okay. So what I was talking about, you see this kind of a structure. There are many structures. So there is a capacitor and there is a Josephson junction. So this is the region where we'll have a Josephson junction. There is one Josephson junction, another Josephson junction, another one, and another one here. So the capacitor is there, and the connection between each qubit is done through some kind of a waveguide or some kind of a radio wave going from one point to other point. Okay, so this is how at the moment the research wise the quantum hardware developments were taking place. Okay, so this is a potential energy curve corresponding to LCR circuit. In the case of pure LCR circuit, the moment I have a Josephson junction instead of inductor, this curve would become a sinusoidal curve. That's why I'm just drawing this curve. So what matters for me is this location. Okay, so there is also exist another states here. That doesn't matter for me. I can always confine to particular location with particular flux, means particular energy flux onto this LCR circuit, right? So in this way, working with a single atom, naturally occurring atom, to realize a qubit is becomes tough, because that amount of temperature maintained for this to work is in millikelvin. That is not a zero, absolute zero. So that's not possible every time. So if I have an artificial atom which can work with some millikelvin, so I will pour cryogenic liquids like liquid helium and nitrogen and bring down the temperature of these circuits and create artificial atoms and work with the atoms to do quantum computing, right? Okay, so that is about the application. Sorry, that is about the understanding of quantum computing, hardware wise and the software wise. Okay, so the applications. What are the basic applications one could have? Right. So by nature, quantum computing can process multiple times at a given time. Means multiple processing is possible. That is a kind of a parallel computing. And the storage space is also vast with just a few atoms, you can realize. That means I can have lots and lots of speed up. Okay, so right now the artificial AI, artificial intelligence and machine learning is booming up research area. So if I have a quantum hardware with the proper algorithms, I can always accelerate AI and machine learning techniques to have much more like advanced ideas. Okay, so I was mentioning about quantum chemistry earlier, that is mimicking nature. Means if you can model a quantum computing model which can mimic how human tissue reacts with a chemical, okay, it becomes easier for you to design a drug, because obviously you design a drug and experiment on some kind of a person or some kind of animals. Okay, testing, right? So that you can do it in the model wise and accelerate the testing process and come up with the results in much quick fashion. So computational chemistry and drug design development is one of the application area of quantum computing. Obviously, cyber security and cryptography, means with the quantum communication, it becomes tough to snoop in to get the information. Suppose if there is a communication happening between A to B, if a third person wanted to steal the information, even though if he is able to steal, immediately the person A and B will know and they will discard that information which is being shared between them, right? So easily the snooping can be detected. And financial modeling is another application. right? For example, you are investing on some particular share, so you would be always checking what are the benefits, what are the profits out of it, what are the possible losses, right? So but you just measure all those things and you will plan, you will always have some kind of a strategy. So having so many different combination features, it becomes tough for you to understand. So in the financial industry, using quantum computing, you can do very interesting things. Okay. And logistic optimization, that is a travel sales problem, means if I had to find optimal solution for a traveler or a salesman to do sales with the less amount of utilization of the resources, in that case the multiple combinations of routes will be there. It becomes tough for a classical computer in a way to find the solution. But with a quantum computer which can access all possible solutions at a time, so quantum computers can again outperform classical computers in this kind of a logistic optimization. So weather forecasting is also another interesting area where quantum computer can do interesting stuff, because weather forecasting always carried with the processing of huge amount of data. So that is limited with a classical computation handling a huge amount of data. So with the quantum computers, that limitation could be eliminated. Okay, so these are the applications. If I have to give a research opportunities for a computer science or a electronic side area, so one would be quantum error correction. Means when you take a hardware, do some kind of a quantum processing, always there are errors. So right now whatever we have is a near people call moderate error quantum computers we have at the moment. So full-fledged error-free quantum computers we don't have as of now. So one could work in that area. So fault-tolerant quantum computing could be area where people can work and progress. Okay. So obviously quantum algorithms, whatever algorithms we have is hardly few in number. So you can always come up with new algorithms where interesting things, useful things could be carried out. Quantum cryptography, right? So with conventional cryptography, people are working with the quantum hardware included and quantum technology, quantum software included. You can do much better things, right? So again, it is also connected to quantum communication and quantum sensing. Quantum sensing means the sensors could be designed with the quantum hardware, so which could be much more accurate in comparison to the classical ones. Okay, quantum materials is in a way hardware research. So obviously people are working for getting novel materials like which can exhibit superconductivity at the room temperature, because whatever Josephson junction we are talking about, it is consisting of superconductors which needs a cooling to millikelvin, right? So that's why you see IBM quantum computers having a huge drums, so where the circuit would be put and the cryogenic liquids will be circulated to reduce the temperature to millikelvin. Okay, if I have a room temperature semiconductors, that means I can eliminate that cooling requirement. I can have quantum computing at the room temperature itself. So in that way, quantum computing applications or opportunities could be explored. Okay, so that's about it from my end, right? So if I had to list out some key players in quantum computing as of now, right? So hardware wise, there are quantum annealing technique. The D wave is the one which is mainly aligned or based on quantum annealing. There is a one technique. The other one is photonic quantum gates or photonic quantum hardware with the photons. A Canadian company, Xanadu, and Google and IBM and other Intel and Rigetti, and these guys were based on superconducting architecture. That's this one, okay, LCR circuits, right? So trapped ions, ion Q, and topological device, topological quantum it's an area we have to do with quarks, right? Quarks is another right? So it's advanced area. I'm not touching it. So as of now, Google and IBM are actually leading the way for quantum computing, right? So that's about it from my end. If you have any questions, please ask me. I'm happy to answer.
So I request the participants here to ask their questions by unmuting themselves. Also, they can ask or they can type it on the chat window.
Dr. Aswath?
Yes, sir.
Hello?
Yes, sir.
Yeah. It was a very good presentation. I just again heard back about quantum computing, which I got introduced some 20 years back. So it was quite refreshing. But over these years, I think quantum computing is it application specific, or can I have a generalized computing system like what we have today, classical desktops and all those things? No,
Right. Yeah. Thank you for the question, sir. Yes, this is a question always asked to everywhere, to every person who is working or associated with the quantum computing. Yes, as of now, I should say quantum computing or a quantum hardware in its very infant stage, right? So infant in the sense doesn't know anything, only it is growing, right? So like 60 years back, when the people were looking for a classical computer, which were of the like sizes of rooms, right? So that time they didn't even realize that this can lead a path to so many great things, right? So right now, whatever quantum hardware or quantum software or algorithms we have, they can only do some certain specific tasks only, right? So with the development in tolerance, the error-free hardware and advanced quantum algorithms, so we can have generalized commercial quantum computers where people can use for multi-purposes. See, if I take a laptop, right, this laptop or a personal computer could be used for even non-technical areas. For example, right? So the quantum hardware, whatever developed so far, is not at that level. Okay, it is like specific. It is task specific. So, for example, if I want to do some factorizing, so I can use a Shor's algorithm, right? So for certain order only, the number wise. So because the limitation, the qubits, whatever qubits we can have, error-free qubits. If I take like IBM labs, so they have about 65 qubits, right? 65 qubit quantum computer where you can access through cloud and do some quantum computation. So it is limited in that context. So by 2030, I think IBM wanted to go up to 300 qubits or so. And if I take a D-Wave, they who are based on quantum annealing hardware, so they were about 1,000 qubits. But only thing is, again, only those computers were, this D-Wave computers were they can only do optimization technique, right? Task specific. So in that way, now whatever computer hardware, quantum computer we have, a task specific. So universal quantum computers are not yet designed yet. Okay, so
thank
it is
you,
on the
sir.
way.
Thank you.
Lots of progress is taking place. Okay, so every day a new thing is coming up. For example, I think a few days back, I think our DRDO, they have announced quantum cryptography, like key distribution, about 100 kilometers, right? The first, the interest, like a powerful result was in Spain. I think they did it for 140 kilometers, quantum key distribution. So India is also in the same path, right? There is a lab in Bangalore, QNU Labs,
Okay.
right? So they actually give a service for a quantum key distribution. You can have between any 2 points with the quantum communication. So no third person can snoop in and extract the information, right?
Okay.
So
Okay,
this,
sir.
again,
Okay.
it's a task specific. So generalized quantum computers, universal quantum computers are not designed yet. So those are on the pipeline.
Thank you. Thank you, Professor. Thank you.
Yes, sir.
Any question? Any more questions?
May I?
Yes, sir. Please.
Sir, I had a question regarding the newspaper.
Sir, can you come a little bit near? The mic is maybe a little bit far.
Yeah, yeah. Keep mic close to your mouth.
Am I audible?
Yeah. If you keep it near, yes, you are audible.
Yeah. In the newspapers and all, they just give that the quantum supremacy is given by Google and sometimes
Yeah.
IBM.
Yes.
And does Indian researchers who are working in quantum computing, do they involved in such quantum supremacy issues?
Right. Thanks for the question, sir, Dr. Kumar Swamy, sir. Let me tell whatever I know regarding quantum supremacy. So Google has just executed a task on a quantum hardware with 54 qubits, right? So among that, I think 2 or 3 qubits were not working. So only 51 or 52 qubits were working. So among them, they did something called probability distribution spanning. Means you take 52 qubits, do something, some task you do, right? So on a regular classical computer, if you perform that task, it will take about 10,000 years. Okay, right? So on a Google, this quantum computer, there is a name, I forgot the name that for that quantum computer the Google has executed. So they did it in like a few hours or half an hour, I don't know, something like that. So right now there is no direct application for that task. Okay, so what is the motto of performing or executing that task is showing that whatever the quantum computer is doing in few minutes, the classical computer, even the biggest classical computer, the IBM has a Summit, I think, even that would take 10,000 years, the classical computer, to perform that task. Okay, it's called probability sampling. Okay, so there is a Glodden board or Glutton board is there. I'm not getting into that. So it's probability sampling. You take 52 qubits. There is some kind of a probability distribution among these 52 qubits. So that probability distribution, if you want to sample on a classical computer, it requires computation time of 10,000 years. So classical quantum computer can do it in few minutes. So that's a quantum supremacy Google mean. But later on, IBM actually stated that their computer can do it in a few days' time, I think. But still, there exists a difference between classical and quantum computers. Okay, so IBM and Google, they're like Westerners. They started working in like 10 to 15 or 20 years ahead of us. Definitely, they are leading the path. So Indian context-wise, we are not at that level. So hardware wise, hardly few groups are working in that. One is in TIFR, one is in Raman Research Institute and ISC, right? So more or less all other research areas, research going in India is on software. Okay, so quantum computing tools and something like that. Okay, so still we are a little bit behind this Western research. China is also leading more or less neck to neck with US, right? Okay, so India is a little bit behind. I don't think India as of now can show some kind of supremacy, quantum supremacy results in current time. Okay, it may take another year or so for that.
Thank you, sir.
Yeah. Right. From the chat box, I'm looking at Mummadi Swati is asking, I have a doubt regarding quantum error correction. Okay,
Hello.
so I don't know what is the doubt. Let me tell what is
Hello,
the
sir.
error correction.
Sir, can I speak? Am I audible, sir? Can I ask, sir, doubt?
Yes. Yes, you can.
Yeah. Good evening, sir. I'm Swati, sir.
Good evening,
Sir,
ma'am.
I have done where can we apply quantum error correction? Do we have any real-time applications for that?
Yeah, see, when you design a quantum hardware, right?
Yeah.
And then do some, this like you come up with some strategy of working with that hardware. That is an algorithm, right? So algorithm has steps in between where some gates will be there. There is a processing happening in between. That means a quantum state going through a quantum gate comes out, right? So suppose you intend a quantum state goes into a quantum gate, it should become B, right? Instead of it is becoming B, right? 80% it comes as a B and 20% comes as a C out of 100. So there is a 20% error.
Yeah, sir.
You
Yeah.
see? So the quantum error correction is nothing but eliminating that C. So if I take any now go platform of this Google platform, Gmeet or WebEx, so in the settings you see there is a noise cancellation. So what this noise cancellation does is it finds out what is the noise range, what is the phase of the noise, and it will add same noise with a negative phase, so that noise will be eliminated. So the quantum error correction, error correction is nothing but you find out the noise, what is the noise, how it is created. Okay, so you somehow mitigate the noise by doing the quantum error correction. So it's a highly sought research area as of now, because the hardware is developed technically and the software is there, but only thing is you have to mitigate the errors happening in between. So yes, hardware wise, the area wise, it is actually implemented hardware at the end of hardware as well as the software. So your algorithm should be error free, and if there is an error occurring in the process, that should be eliminated. Okay, even the hardware wise also people are doing research. Yes.
Yeah, sir. Sir, actually, I'm working in that area. So actually, my problem, where I'm getting problem is we have implemented some error correction method. So
Yes.
practically, can we apply that on any real-time application, like any switches or routers? As of now, no quantum switches or routers are available practically. Can we either by using the simulation tools or anything? Can we?
Yeah, yes, absolutely. Yes, you can apply. Yeah.
Okay. Okay, sir. Okay. Thank you, sir. Thank you so much.
Right.
So any more questions? I think, yeah. So sir, Ashwath sir, thank you very much. This was a wonderful webinar from you. And I think all the three objectives are met. You have given sound discussion on fundamentals, where discussion on gates was introduced, and about the hardware implementation of the quantum computers were also being introduced by you to the participants. The objective is very clear. We need to take algorithms and implement it for the quantum computers. So I hope that all the participants enjoyed their evening with this topic. So feedback link is there in the chat window. So those who have provided, you can ignore it, and those who have not yet, please provide your link. And resource person, the Dr. Ashwath has also posted his email ID for any questions. He will be, free to answer you. Oh, sir is also giving his mobile number.
Yeah.
Very, very, very nice of you, sir.
Yeriswamy, I have one request. Can you arrange for another 45 minutes to 1 hour talk on mathematics in quantum computing?
Yeah, yes, sir. Yes, sir. Definitely.
We shall request him, no?
Yes, sir. We can, sir. Yeah, we will do that.
Is it a feasible one?
Yes, sir. Definitely, because about the matrix operations, many of the people will get, their basics refreshed.
Right.
Yeah.
So you're asking me, or should you will be asking?
Yes, for you only, sir.
Okay.
Can you deliver 45 minutes lecture on mathematics useful for understanding the code?
Okay.
This talk itself would have done it in 2 phases.
Yeah,
Yes.
that's what I'm thinking, sir.
2 to
Yeah.
Okay.
It's
So-
almost 2 hours lecture, sir.
Yeah.
Very wonderful, very wonderful.
Yeah, very wonderful, mind blowing.
Yeah. So Mummadi Swati, I think I got to know that you I don't know, you or somebody else. Maybe you can just contact me regarding this quantum error correction. We can have a further more discussion so that
Yeah, sir. Yeah, even I think you know me, so I'll contact you, sir. I'll contact you.
right.
I
Yeah.
think ma'am was there in the quantum computing FDP in Atal
Yes.
program.
That's what I
She was
recall.
also there.
We actually mailed, communicated in between, I guess.
Yes.
Yeah,
Okay.
sir. Yeah, sure, sir. Sure. I'll contact you, sir. Thank you, sir. Thank
Okay.
you so much.
Okay. So, Ravi sir, shall we wind up?
Yes, sir.
Yeah. Please proceed with the vote of thanks, sir.
Okay. Thank you, sir, for your very informative session. I request Anami sir to say few words in short 1 or 2 minutes, sir, please. Anami sir.
Proceed, sir.
Yes,
Sir, he has to come very close to mic.
Ravi sir?
Yes, okay, sir. Thank you. I request Eriswamy sir to thank the for hosting the session. Please proceed, sir.
Sir, I thank all the participants to attend this event, and especially the undergraduate students who have shown interest for such a long time period. So thank you very much. And I sincerely thank the resource person, Dr. Aswath. I would really heartily thank our principal, Dr. Baswaraj Anami, and is also the IEEE NKSS president. I thank the secretary of IEEE NKSS subsection, Mr. Ravi, the execom members of the subsection, and also IEEE subsection for providing us with this facility of WebEx. I should thank Mr. Chengappa who replied immediately with all the requested IT infrastructure. So I thank all the members who have supported, and I request all the members that please join us in our future webinars also. So thank you very much, sir. Thank you.
Thank you, sir. Thank you.
Okay.
And
Thank
I
you. Thank
request
you.
all-
Thank you very much, sir.
Thank you,
I
sir.
request
Bye,
all
sir.
the participants to unmute their video, please.
And I just take a privilege to thank all the organizers and inviting me for this. It was very pleasant and enjoying for me as well. And shortly in June or July from IIIT, we are conducting a workshop, and wherein we will discuss little bit fundamentals and the software wise programming also. So we'll be circulating the information to Eriswamy sir. So undergraduate students wise, those who are interested can join for that workshop. So we'll be discussing hands-on quantum computing programs and other things.
Ashwath sir, can you this one stop sharing the screen so that we can get that group photo?
Yes.
Yeah, now it is good.
Sir, you are taking?
No, yeah, I took it. Wait, sir. And Ashwath sir, where is your video? I could not see you. Okay. I took it.
Yes. Thank you, everyone.
So thank you very much, all of you. Have a nice
Yeah,
evening
thank
and
you,
weekend.
everybody. Thank you,
Nice.
everybody. Thank you.